Welcome to Lunch with the Core. Today's speaker is Mahrous, and he's speaking about some work he's done in the core with the X-ray CT system and also our
serial block scan.
Serial block face electron microscope system. Tomorrow we are having a MinFlux workshop, and so that is MinFlux, if you're not familiar, is a fluorescence technique that gives 2 nanometer resolution in X and Y for imaging. And so we're going to do that tomorrow morning. The talk start at 9 o'clock, and we have a bagel before that. So,
thank you so much. Thank you so much, guys, for coming today. I will start giving a little bit introduction about myself. My name is Mahmoud Mahrous. I am a PhD student at Civil Engineering Department, and my professor, I work with Professor Ivona, and our work that I will demonstrate today, the title of the talk can give you an idea about what I'm going to do. It's just only we try to do like different kind of microscopes to be able to image different structure in the hoof wall. So as you can see here, this is the hoof wall. Maybe some people are not very familiar with the word hoof wall. So this is the hoof wall that we are working with. So this little tiny thing in the bottom of the feet of the horse is the work that we are doing. So the outline of the talk, as you can see, I will give a little bit introduction about the work and then some background information to enhance the understanding of what we are doing. I don't like to jump into what we are doing immediately because some people may be not familiar with this kind of stuff. And then I will give you an idea about what we are doing exactly and our current work and the future work. So here is our research group. We have a collaborated group from UIUC, led by Professor Ivona, and this is and this is our group in the bottom here. This is me. And then our collaborator is from UC San Diego, is led by Professor Mark Meyer, and other 2 students from there, Ben and Audrey. So what we are doing, our group, so I will give you a little bit idea about what we are doing in our group related to this project and other projects. So mainly, we have 3 different disciplines that we work with in this project. First part is mechanical testing. So we mechanically test the hoof wall, what the hoof wall is doing in mechanical, or the mechanical behavior of the hoof wall. And the second thing is microstructure characterization, which is the part of my work that I'm doing and what I will show today. The third part is collecting these 2 different, so we collect the information that we gather from here, the mechanical testing behavior and the microstructure analysis or microstructure behavior. And then we do manufacturing and 3D printing, and then we test what we found there. So as a part of bio-inspired work, which is very famous now. Everybody's trying to imitate what is in nature to improve the materials and improve a lot of other stuff. So this is our work. So what will be the application for our work? So one of the things that I always have a problem with when I go to any seminar or any work, like many times, they will jump immediately to what they are doing, but we don't know what the applications. So you are doing XRD, but for what? What I will do after I learn this kind of stuff. So the application of our work, we will the work we will do is giving can be used in doing this helmet because it has viscoelastic behavior. It can sustain high impact collision. And the other thing is space application. So it could be used also for this kind of application in the space. Like as you can see here, there is a problem in the space shuttle here and in the space station. So and one of the very famous stuff, very famous problems that we have seen a lot in the news and the media, this kind of problem that happened when the bird hit into the airplane. So this kind of work that we are doing also can improve this kind of problems or solve it. And the other thing is the collision application for cars and so on. So let's have a look at what other people have done already, following the same stuff that we're doing. As you can see here, this is very famous dog, or they created at Boston Dynamic. So now in the American Army, they started to have thousands of this to use in war. They just only imitated what is going on with the cheetah. So the second one, as you can see here, very small, tiny robots, or as like flying insects. This one is very famous as well. They just only imitating the salamander thing. So they were trying to imitate or mimic how the salamander walk. So they can make like this kind of structures, can go over the walls, can walk upside down and stuff like that. This one also, I was fascinated when I know that B-2 bomber, one of the most advanced bombers in US Army, is exactly the same like Falcon. So they studied the Falcon and they did exactly the same thing. This one also, one of the famous stuff that happened in Japan, they were having a problem with the bullet train, very fast train. When this train comes out from the tunnel, it has very huge sound. It makes a lot of problems. So they started to study this kind of bird. What they found is they found that bird goes into water without doing any splash. So what they did, they characterized the nose or the mouth of the bird, and then used the geometry for the bullet train, and the problem is solved. So bio-inspired is a huge field right now. So we'll give you an idea why we are caring a lot about horse hoof. So if you told anybody, like one of my professors, I told him, I'm working with horse hoof. He said, what you're doing with horse hoof? So the motivation behind the horse hoof, that as you guys know, the horse is almost like a half ton and can jump and can walk in irregular earth shape, and is not breaking and can withstand this huge weight without any break, without any problem. So this high impact resistance properties in the hoof attracted a lot of researchers to study what is going on there, because if you understand the materials or how this structure is built, you can make exact the same thing, a kind of materials that can withstand the high impact forces. So just to give you an idea about what other people did before us, so we will show why we are doing this and others, they haven't done this. So one of the very famous paper, it's the thesis of Leach. It's almost like the Bible of horse hoof. He was one of the first people that examined and studied intensively the horse hoof in two directions, in microstructure direction and in mechanical direction. So this, if you try to publish any paper without mentioning him, they will reject the paper automatically. They will not look at it. If you did not put something from this, you don't know nothing about hoof. So this guy, it's 1980. He mainly used regular light microscope, because this kind of advanced microscopes was not famous at that time. And he did also use some scanning electron microscope. So the second guy was also very famous in that field. He came after him, was Gaspy and Goslin. He also, he did something new more than the previous guy. What he did is sectioned the horse hoof in 6 different regions, based on the structure, based on the amount of tubules, which I will go on and I will speak about in a little bit. And then he also, for the first time, he was, not first time, but intensively, he measured this area there, which is called the tubule modular cavity, which is the main work for in our research, or my work that I will show today. And his work mainly also was only using mostly polarized light microscope. And he did also the second paper in 1999 was mostly mechanical behavior of the hoof wall. So also everybody working with this kind of materials has to go in 2 routes, mechanical and microstructure, because both together they give you an idea. So, and then this guy came in after him. he proposed, or he said that these tubules that I mentioned before here, he said those tubules are completely hollow, which we will try to see if this is true or not. And also, he said that the tubule modular, this part, or this empty area here, is around 2% of the whole volume of the hoof. And he also said, which is right, that the tubule at the beginning of the hoof is denser, or the amount of tubules at the beginning of the hoof is denser than as you go inside. And also this we will show scientifically now why. And then his work also mainly light microscope was the only light microscope. So as we advance more, this is almost 2019. Hong and his colleagues, they did a beautiful work and a very amazing paper that he started to use micro-CT scan for the first time to analyze the hoof, as you can see here in the side. And he used multiple kind of microscopes, ranging from scanning electron microscope to TEM and so on. And he come up with, and he said, or he concluded that the volume of those pores or those modular cavities are around 3%. And the area or the diameter of these holes is around 41 micron plus or minus 9. So he also did a lot of work, mechanical work, complementary work for the microstructure work. And then for the first time, he started to speak about the bridges. Bridges, we will show now what are the bridges or what they do. So this is one of the last paper that our group published with one of our colleague in UC San Diego. He did beautiful work also using micro-CT scan here, and he characterized the hoof, the bridges inside the tubules, and he was able to calculate or to quantify the bridges width and density and the tubule density and this pocket and the volume of this pocket. And he also used mainly micro-CT scan and scanning electron microscope. So what we will add. So to give you a little bit idea about the horse, what the horse feet or horse hoof is made of. It's mainly made of keratin, like hair. And when you go through the papers or review papers about the keratin system, you will find majority of them almost the same, very close to each other. So you can see here, this is a horse hoof. It's almost the same structurally almost the same like the sheep horn. So it's exactly the same if you look up and down, and we will go now more in depth on that. So because of its keratin system. So here's the good stuff, our work. After I gave you the idea about what is going on, we will show what we exactly did at what we improved. So the horse hoof is similar like your human bone. So your bone is exactly the same like the horse hoof with differences, but the point is it's a hierarchical structure. So as you go down, there is another scale, another scale, another scale, multiple scale. Each one of them has his own mechanical properties and structural properties. So you can see here in the top, this is how the horse hoof look like. And we extracted a sample from the hoof like that. And this is like 3D model for what the hoof look like. And you can see here the tubules are more dense outside in the outer part of the hoof. And they increase in size but reduce in number as you go inside. And this is at the mesoscale. And here is the part of this area which is showing here is the modular cavity and the tubule wall. And after that, if you go more in the higher or smaller scale, you will start to see the lamella, which is also part of the hoof. And it's around 10 to 40 micron. And if you go more into the lamella with higher magnification, you will start to see the microfibril, which is mainly composed of intermediate filament. Intermediate filament is just like reinforcement inside this microfibril. So this is how the hoof this little thing in the bottom of the feet of the horse look like and under microscope. As you go more, you will get more details. So we'll give you, I don't know this is offensive or not, but I will just show you how it's difficult to get this horse hoof or the horse hoof out. And in the meantime, when you look at this, here, you will see how it is very tough to cut with cutter. It's very, very tough. We spent like 6 hours trying to extract this. So it is not easy to cut it because of all this stuff that we mentioned before. So as you can see here, the beautiful horse, we extract this little bit, this horse hoof out, as you can see here, and we cook it with CT scan, with micro CT scan, and you can see those images. And here, in our work, when we did the analysis using micro CT scan, we did it in 2 different levels. One of them was lower resolution, which is larger thickness, which is around 13.35. We did this beautiful work here in the core using the micro CT scan here. And you can see here for those maybe not familiar with the CT scan, these are the axial cuts or the images that the raw image we get from the CT scan. And then here we reconstruct those images in 3D, like here, using Amera software or any other software. But in this work, we used Amera software. And then as you can see here, you can see the tubules are very clear. They are very parallel to the axis, to the longitudinal axis of the horse hoof. And here it's a top view for this cube here. And you can see it's very dense. There is a lot of them in very tiny area. And as you go more into more magnification, you can see here, you can see that the tubules, I don't know, you guys can see it very well, or we can close the light. Can you guys see? So, as you can see. So here, you can see, oh, now I think it's way better. As you can see here, you can see the tubules. The tubules are parallel to one another. And then in the top here, you can see like little waviness in here. And with a little bit magnification, they are very clear that there is waviness in the tubules. And one of the things that I mentioned before, one of the previous researcher, he mentioned that it's a hollow structure. But in these images, we can see very clear that it is not a hollow structure. And there is like air buckets, and there is a bridges in the middle here. It's almost like a spring. So there is this continuity inside the tubule, discontinuing this part from that part here in the middle. And there is a lot of research in our group also trying to quantify this and see the effect, the mechanical effect of these bridges on the mechanical properties of the hoof. So this, it's a big deal. So this kind of work is a big deal because we are taking this information and putting them in the 3D model and try to simulate what is going on, if these bridges are there or not, with different angles. All this kind of parameters, they are changing the mechanical properties of the hoof. So, as I mentioned in the beginning, we went with low resolution, very high magnification, and now we are trying to zoom in more and we tried to do higher resolution micro CT scan with 0.53 micron. And as you can see, the number of the tubules is less. The tubules are very clear, you can see them. But to do that, we try to partition the tubule or the horse hoof in 3 different sections to study each one of them alone. And the first part here, A, is this image here. And you can see the tubules are there, but it's almost semi-full with tissue, or damaged, could be damaged, or semi-full with tissue. And you can see in the bottom here, it's a multiplanar reconstruction image from these images here. And you can see it's the tubule is very clear here, and it's almost full with tissue. It is not completely hollow as they were mentioning before, and all of them almost the same. And as you move inside, you will see that the tubule started to be more circular. Outside here is a little bit elliptical, but as you go inside, it's more circle. And also, we started to see a little bit small, like white tissue there. This is the beginning of the bridges that we have mentioned before. And as you go here, you will see it a little bit clear that there is a start at the beginning of the bridges here. And as you go more into C section in here, you will see it's very clear that it's more circular, and the bridges are very clear here in the top and the bottom. What fascinated me that this guy that I mentioned before, Leach, the guy with the thesis from Canada, he almost constructed the same thing but using histology, or he cut a section from the hoof and he did like microscope, and you can see that there is a lot of tissues inside here, which is maybe those represented here, but he did not mention anything about the bridges. And here also you can see very clear that the tubule is almost closed. Here is an image for a scanning electron microscope, and you can see this tubule here is empty, but as you look here, there is something inside, which it could be a bridge. And a higher magnification image more with for the CT scan, you can see it very, very clear that there is bridges here, or discontinuity. So we moved more forward to characterize these tubules or these cavities in a statistical way. So we can, when we do the modeling, we will know if, because as we found out that if we put circular shape there in our materials, they behave differently if it's elliptical. So we tried to know a lot of information about it to characterize it. So what we did is using the Amira software, we were able to calculate multiple things. One of them, the equivalent diameter of this modular cavity. And you can see here, the modular cavity before was calculated with large variation. But here, what we found is that the average of, one of the things that I need to mention is the beauty of micro CT scan is that you can analyze thousands and thousands of tubules, not like the other previous work. The previous work before, just only like a light microscope and someone sit there and then count by eyes. Sometimes he get drowsy or dizzy or something, and he would not count nicely and 100%. But the good thing about the automated way that we used here, that we were able to calculate or to analyze 3,905 tubule, which means it's a higher intensive kind of work more than the previous people did. So, and what we did is, what we found is that the equivalent diameter, the average of the equivalent diameter is around 69. The previous work was very different between someone and the other. So as I mentioned before, one of them is 41 plus or minus 9, and the other one was 200 micron, and the other one is 300 micron. So this variation in this analysis, what leads us to do something like that to make sure that this is the right way to do it. And also, this variation could be one of due some reasons. One of them, the sample location, because if you get the sample from different location in the hoof, will give you different criteria. And also the characterization techniques, as I mentioned, if you use your naked eye, you will have a problem because you will not be perfect. And the nature of this horse came from where? So how the environment that the horse came from also can affect this kind of work. But in our work, what we did, we extracted 5 different samples from 5 different locations, and we did the analysis based on multiple resolution with different length, and then we did this kind of analysis. So for the equivalent diameter, the average is around 70 micron. Here, the second thing that we did also the surface area, and we calculated the surface area or the porosity based on the surface area in 2 different ways to make sure that our work is right. One of them is 2D, and the 3D. And there is difference between them. So in the 2D, we found out that the porosity is around 3%, which is correlated with the previous people did, which they used also micro CT scan, and it's around 3%. And the average of the surface area was 3.55 times 10 to 4th micrometer square. And but when we did the porosity volumetric porosity, instead of using 2D, we used the 3D. We started to see something different, that the porosity increased. And in literature said it's in 3D is more accurate than 2D because in 2D the instrument or the software is only measuring the radius of the particles that was analyzed, and this radius could be anywhere. So this variation can happen because in our work the hoof or the tubules are not perfect sphere or perfect circle. So when the software can measure anywhere, so that's why it gives this little variation. But in 3D, when the software calculates in 3D, it calculates based on the voxel size. So it's more accurate. So we started to see 3.47%. So the sphericity also, one of the things that we introduced here, previously they were calculating the sphericity using the major axis and the minor axis. Someone also, again, sitting and looking under microscope and trying to measure the longer axis and minor axis of this tubules and characterize it and put numbers for it. The good thing about this, in a matter of minutes, we were able to know the sphericity of those tubules, and we found out that almost 65% of these tubules have the sphericity of 0.86. And the other thing is, if you look to the variation and the numbers here and the values here, we cannot say that the majority of the hoof is spheric, has a spherical shape or elliptical shape, but it's integration between both of them. And one of the things that I have noticed when I was preparing this presentation, that what I found is that in all of the previous measurements that we have done, we can see gradient in all of them, all measurements. So there is like variation in sizes, variation in shapes, which I think this is one of the things that makes the hoof mechanically important, because there is variation. So each scale can help in mechanics. This is what I think. I'm not 100% sure. I have to dig through and understand more, but this is what something captured my eyes when I was doing this kind of analysis. So the good stuff is this serial plug scanning electron microscope, which was recommended by Dr. Glenn. I have no idea about it before, but upon discussion, this is the beauty of discussion with a scientist. He gave me this idea, and Dr. Kinsley, I don't know if he's here or not. Dr. Kinsley, he did great work with this one. He spent too much time in the lab trying to prepare the sample, because this kind of samples is very difficult to work with because it has some elastic behavior, so it's very difficult to cut. So as you can see here, we cut a small sample, like 2 by 2 by 3, and then we embedded the sample in epoxy, and then we treated the sample with this different kind of chemicals, and after that we sputtered the sample with sputter coating, just to remove the charge and to make nice image in the scanning electron microscope. And this is, we end up with this number of images. It's around 1,200 something image, and you can imagine, or I think the good description for this instrument is just only 3D TEM. So we are just trying to get, we got a lot of images, and we built 3D model out of it, and without any human interaction. So if you need to do the same thing using TEM, you will spend hours and hours and hours, and your work will never reach this, because in regular TEM, it's very vigorous to prepare the sample, and you can destructively destroy the sample. But here, the machine automatically is doing that. And then from here, you can see that this is the tubule or a modular cavity, and we started to see something fascinating, which is at the nanoscale. Just to give you an idea what is going on, is this white color is the pores where the epoxy penetrated through the structure and stayed there, and this is soft tissue around it. So this white stuff, if you look carefully around here, this part here, you'll see that in the hoof wall or in the tubule wall here, there is some white stuff here, which means that the tubule wall itself is not solid as other people thinking, and in the same time you cannot see it with regular microscope, a light microscope, and also you cannot see it with a regular scanning electron microscope. So when we go for higher magnification, we started to see that, and we will see the effect of that later on. So that is the good thing about this kind of instrument. that we were able to construct these images and get this new information. And in the same time, you can see here in the right side up there, we can see clearly, like even the cell boundary, which is not easy to find with TEM because the sample in TEM is very tiny, and you cannot see it beautifully like that. So to confirm the finding that there is pores here that was not being captured before with a scanning electron microscope or light microscope, if you go more, we tried to go more, and we used something never been used before maybe in biology, I don't know. But this instrument, usually we use it in concrete, since my civil engineering background knocked in, and they said, let's try this. So to confirm that the porosity that we got is right or not, after we found there is some tiny pores there, especially in the leach thesis, they mentioned that there is permeability in the hoof. So, which means if there is permeability, so there is a structure there and it's permeable. And we can see that the tubule is not permeable because it's discontinuous. So from where this permeability comes? So what we did this helium pycnometer in the civil engineering department. In short, we calculated the porosity based on helium gas. So we cut the samples, and then we put them in water for 24/7. So all the pores inside the materials will be filled with water, saturated. And then we put the sample inside this instrument, and then we measure the volume. So now we have the external volume without any voids inside because it's filled already with water, so the helium will not penetrate through. And then we take the sample out, dry it, and then weight it, and then put it again in the instrument, and then subtract with this formula there, and we were able to calculate the porosity as you can see here. Boom, the porosity changed, and we have higher porosity in all of them, almost 8%, which means that this technique confirmed what we have seen already before on the previous one, on the serial plug scanning electron microscope. So every work have been done before. They were only looking at this tubule modular, but they were ignoring these tiny pores within the tissue of the hoof wall. So in the end, the other thing that we are currently working with was Dr. Austin. I don't know if he's here or not, but we are working on the doing second harmonic generation to characterize the intermediate filament that I said they are the reinforcement for the tubules, and we are trying to characterize the orientation and the numbers and in different position in the hoof wall, and this is our work currently. And here is the conclusion is that micro-CT scan was used very successfully to characterize or to quantify everything related to the modular cavity. And the second thing is serial block scanning electron microscope also was very successful technique that showed us something new, which is the nanopores within the wall of the hoof wall. The third thing is helium pycnometer was also utilized successfully and confirmed what we have seen before on the serial plug scanning electron microscope. So in the end, I would like to acknowledge Professor Ivona for her support and giving me the chance to work in this project, and all my group members for their help and advices. A special thanks for the people here in the core, Dr. Glenn, Dr. Kinsley for sure. Leonardo is not here, and he also did a lot of work with me in the micro-CT scan part. And for sure, Dr. Austin for his great work. And we cannot forget NSF for their generous money that makes our work happens. And in the end, thank myself for this beautiful presentation. Thank you so much.
Other questions?
No, thank you. I answered everything. Why questions?
Just a general question.
Sure.
I wonder for these group like this, are they the same density or the same microstructure across horses species?
In all horses, you mean?
For horses, yeah.
This is one of the things that I mentioned in the presentation, that for sure all of them are almost the same because it's the building block of this hoof is keratin, which means all of them almost the same. but there is some differences between them based on the number of the tubules, the geometry of the tubules, the arrangement of the tubules based on the environment they are coming from. But I think, or I believe in that, because since they are keratin, all of them is keratin, so all of them will be almost the same building block. Did I answer that question? Amazing. Any other question? Yes.
For the porosity test, do you think the tissue that's in the pores could affect that? Like, I'm just imagining them like hydrating and getting fatter and then dehydrating all like shriveled up.
Yeah, that's a beautiful question, because to solve this problem, I did this experiment maybe 5 times with different temperatures. And then in the meantime, I took the samples and I did micro-CT scan to make sure that there is no fractures there. Because as you hydrate this kind of materials, since they are having viscoelastic behavior, so when they shrink or when they dry, they might crack. So those samples I tried many times. I tried at the beginning 105 degrees Celsius for 3 days, cracked, everything was not working. After that, I tried 80 degrees for 3 days, it didn't work. I also started to find a lot of cracks on the sample, so I removed it. The third thing, when I was doing this, I put it at 80 degrees C for 24 hours. We started not to see any cracks. And also logically, if any extraneous value we have seen there, for example, if all of them like 8.7, 7 point something, 6 point something, all of them in the same range, makes sense. But if we find something 20, means this is extraneous, we can take it out. But I did not take this route from the beginning. I tried to try multiple temperatures until I reached this very close value. Make sense? Yes, sir.
Were you looking at horses that were unshoed, or does shoeing a horse with metal horseshoe change the structure of their bones?
That's a good question, but those horses, they have shoe. But what we do is, the shoe has like a limit inside. It's like 2 centimeters or something like that. And what we did, we cleaned up this part. And as I show it, that's why I showed the video at the beginning, how we cut it. We try to remove anything that is not, it's abnormally or was introduced in the wool itself. So most of them, when I was taking them from the fridge to cook, so some of them, they were having a lot of shoes and stuff, but we removed it to make sure that we have homogeneous kind of samples.
Well, I guess this question is, if you were to do the same analysis with your horse, that has never happened where
Anything abnormal happen, will make a difference for sure. But again, we are to make our work right, we try to remove anything abnormal happen to the horse. So we try to take samples from far from this kind of areas. Because as you know, maybe that's why when I mentioned that the environment that the horse came from, also some horses, they have disease. So we cannot go to the diseased area that already cleaned before and sanitized and stuff, and then do the analysis. So we try to go away from this kind of problems to make sure that this is the natural horse hoof that was there. Can I eat? No? Any question? Just clap for me. That's all. Thank you so much.